Good morning. I am GJ van Westhuizen, student number 4555355. This is my transportation engineering pavement and geometric design presentation on assessment 3. It was required to do a conceptual design for the upgrade of a gravel road commonly found in rural areas in South Africa to a 4-lane divided road. The road should be between 3.5 and 4.5 kilometers long and should include the design of the pavement structure as well as the geometric alignment of the road, while considering stormwater drainage along the road. The reason for the proposed upgrade is twofold. The R543 is a major route into Mpumalanga from the Free State that can be used to convey goods to the eastern countries through the border at Mahamba, Eswatini. It will also bring more tourism into an area that is known for its game reserves, such as Tala Game Reserve sits there. Yes, and secondly, the road is full of potholes and it is in need of repair. The proposed road lies between the towns of Volksrust and Vrede in South Africa, crossing the Mpumalanga Free State border. The designation of the road is the R543, and the upgrade of the road will start at point A, where the tar road terminates and changes into a gravel road. This is a GPS location 27 degrees 23 minutes 14.1 seconds south, 29 degrees 41 minutes 41.7 seconds east, and end at point B, which is at 27 degrees 23 minutes 2.9 seconds south, 29 degrees 38 minutes and 45.2 seconds east. The designed road length will be 4.86 kilometers long. It's a little bit longer than it should be, but we will get to that later. The area is mainly agricultural and the land agricultural land specializing in maize, sorghum, sunflower, beef, and dairy production. The road has an average height above mean sea level of 1,800 meters. The climate is known as a high-fault subtropical climate and has a high rainfall of above 800 millimeters per annum. It has mild winters and hot summers. The V0 value for the region is less than 2, indicating that chemical weathering will be the main action of breaking down the parent rock. The geology is mainly sedimentary rocks from the Dwaika and Eka subgroup, which forms part of the Karoo supergroup. It is known for its dolerite intrusions in the forms of dikes and sills. The soils that one can expect to find are pseudo-podzolic and vertisols. They are characterized by thick, black, expensive clays that, when they get wet, they can lead to founding problems because they expand. The design standards that was used during the design of the road include TRH-26 for the road reserve requirements, TRH-20 for the drainage requirements, TRH-17 for the geometric design of the road, and TMH-4 for the traffic design of the road. The design data include the weather and rainfall. Importantly, higher than 800 millimeters rain per annum and a V0 value of 2. The average daily traffic at the start of the design process and the CBR values along the center line of the road. An accumulated average daily traffic of 1.507 million vehicles per direction per lane was found to be designed for over a design period of 3 years and a service period of 20 years, with an annual growth rate during the service period of 5%. The delineated subgrades along the center line are presented in the table on screen, with the design subgrade for the required changes. The subgrades varies from subgrade 1 to subgrade 3 depending on the value of the lower 10% percentile obtained from the specific area. A design speed of 100 kilometers an hour will be used on the road, and the geometric alignment will be designed with this in mind. Also, to keep in mind is that the terrain will be mountainous terrain, which will affect the grades of the road. So the road was found to be a Category B road in a wet road region. Category B roads are large rural roads that transport high traffic between major towns. The road will have an ADT of 1.5007 million E80s per lane per direction, resulting in a pavement category of ES3. The region is wet, and the options available for a pavement design that meets these criteria include a granular pavement, a granular cemented pavement, a hot mix granular pavement, hot mix cemented, and a cemented pavement structure. Due to the price of hot mix asphalt bases and the cracking associated with the cemented bases, was a find that the granular cemented base will be the most suited for the pavement structure. A granular base were also considered, but because it's unpredictable, was it omitted in the end. The option that was chosen is a surface layer, which is double seal of 30 millimeters asphalt, a base of 150 millimeters G1, a sub base of 200 millimeters C4, an upper selected layer of 150 millimeters G7, and rip and recompact in situ swirl to 150 millimeters G9. The geometric design was done in Civil 3D. It's a product from AutoCAD developed for the design of civil engineering infrastructure. The horizontal alignment was found by importing the digital terrain model, a DTM, into Civil 3D, drawing polylines along the straight sections of the existing road and joining these polylines with curves of a known radius that fits within the horizontal alignment criteria. For the vertical alignment, was at first necessary to compute the vertical alignment of the natural ground level. This gave me a longitudinal section from where it was possible to insert the points of the vertical intersection, the VPIs, along the road. The curves, geometric points of the curve elements was chosen to meet the minimum design criteria as TRH17. And after the checks for the minimum length of curve was done against the rate of curvature and against the stopping side distance criteria, was these points, the VPIs, adjusted to meet the stopping side distance criteria because the stopping side distance lengths of curves is a lot longer. This means that a lot of the points were omitted in the final design, which created large cuts and folds. The typical cross-section of the road is shown on the slide. Apart from the dimensions of the pavement, which is the 30 millimeter surface layer, 150 millimeter base, 200 millimeter sub base, are there other dimensions along the cross-sectional profile of the road that's also important? These include for the outer shoulder a ditch width of 1 meters, a shoulder of 2.4 meters, and a shoulder slope of 6%. The carriageway width will be 7.4 meters because it's dual carriageway with a crossfall of 2%. The inner shoulder will have a median width of 6.6 meters, a ditch slope to the median of 4%, and a outer shoulder width of zero point 0.6 meters. The Mansell diagram generated from the volume of the earthworks, as well as the volume of the pavement layers of the subassembly that's imposed on top of it, shows large accumulations of cut and fills along the length of the road. This is due to the design speed and the profile of the road. The design speed is 100 kilometers an hour, so the profile needs to be smooth. If these large volumes are deemed to be a problem, will it be required to find a more suitable, flatter corridor that will be able to handle the required four-lane divided road with its geometric requirements? It was required to design an Excel spreadsheet once we were finished with the alignment that can be used to calculate vertical curves and to check the vertical curve calculations that was done in a report by hand to see if it if it's okay. The spreadsheet was designed in such a way that it is possible to determine the change in elevation of the BBC, PBI, or EVC if one of them are given, as well as the approach and exit grades and the length of curve must be given as well. The spreadsheet can also determine the distance along the chain, the distance leading to the change in elevation of the high point on a crest curve or the low point of a sag curve. And the spreadsheet can, by inserting any distance into the for the x value, will be able to generate the change and the elevation of any point along the vertical curve. This will make it easy for surveyors in the field to use it and to map out the vertical curve as they go. Stormwater drainage. There are two drainage conditions that needs to be considered when designing a road. The first is the drainage of the pavement layers. Water needs to be removed as quickly and efficiently as possible in order to minimize ponding of the water on top of the surface. This can lead to aquaplaning as well as the water ingress into the pavement layers that can cause the pavement to deteriorate and degrade. The road must be drained longitudinally as well. The water will be drained from the road surface with a crossflow of 2%, leading to the outer shoulder. From here, it will flow down a 6% shoulder slope to a drainage ditch along the carriageway of the road. The road reserve needs to be drained efficiently in order to prevent water seeping into the subgrade of the road. This can weaken the pavement structure and it can lead to failure. The water will be drained longitudinally by a median drain as well as side ditch drains along the outer edge of the road. Mitre banks will convey the water to appropriate open areas away from the road, from the side ditch drains, and the position of the mitre drains depends on the grade of the road. But it varies between 150 meters and 300 meters along the length. Culverts are used where the road and the natural watercourse intersect each other, with mitre drains depositing the water from the side drain into the natural watercourse as well. Preventions such as hand-packed riprap must be used in order to make sure that scouring of the natural banks are prevented when the water is flowing into these natural courses. So in conclusion, the road to be constructed lies in the Volkshuisvrede area, which is a high rainfall area on the Drakensberg escarpment. Dolerite is readily available for road construction, but care must be taken due to the secondary minerals that can be present in dolerite, which can lead to a fast deterioration. Expansive clays are a problem that might require special attention. And then the designed average daily traffic over a design lifespan of 20 years is greater than 1.5 million, which will give the road a pavement classification of ES3. And from the CVR values obtained along the center line, can you expect subgrade classes ranging from subgrade 1 to subgrade 3? The horizontal alignment and the vertical alignment was done from a DTM on Civil 3D and a Maswell diagram obtained after the typical assembly were imposed on top of the vertical alignment. The cut and fill volumes are large, but this is the only way that the current road corridor can handle the required geometric design criteria. If it is deemed to be too large, it may be necessary to explore different corridors for the road between Vrede and Volkshuizen. In the end was the excess cut volume of 54 meters cubed deemed within acceptable limits to call the Maswell diagram balanced. An Excel spreadsheet was designed that can generate values for the change and elevation of any point along the curve as long as the change and elevation of one of the main points are known, together with the approach and exit grades as well as the curve length. Lastly was a stormwater drainage designed in order to prevent ponding and water ingress into the foundation layers, thereby increasing safety to the road users as well as the longevity of the road. And that is the end of my presentation. Thank you for listening and enjoy your day further.